Okay, so now that we know how to align the EPI with the anatomy and we know how to align the anatomy with the template, let's look at the volreg processing block where we kind of put everything together. As a reminder, I'll just scroll down slowly. Uh, there are a lot of steps that are done here, so it's a little messy, but that's why we have AFNI Proc to write the stuff for us, and then we just have to make sure we understand and concur with everything AFNI Proc is doing here. So basically, we start out for each run. We run 3D volreg to register the 3D T-shift output, the PB01 T-shift output, with our the volume that we just extracted above. The VR at the end of the T-shift block. 3D bucket dash prefix VR base min outlier. That's the base volume that we're aligning to in 3D volreg. That's also the volume we align to in the auto tailor block, of course. So where is it? Dash EPI VR base min outlier. So let's align all of the EPI volumes to our EPI base. And so we run 3D volreg. The prefix for the output, you notice, is rm.epi.volreg. Any file that we write that starts with rm is going to be deleted at the end of this processing script just to save disk space. That's because we don't really care about this. We really just want to know what the matrix is, what are the transformations, and we'll store them in this file, and that's a time series of transformations. So when we align each of the volumes, each of the 150 volumes per run, to the min outlier volume, we save the volreg parameters with 1D file in dfile.say r01.1d, and just to briefly see it. Oh, where's my command window? I think I lost my command window. I will go back in there from my home directory, cd AFNI data 6 /ft analysis /ft.results. Make this a little bit taller. So, and a little bit wider so we get two columns. How's that? Beautiful. So, again, say the input is PB01 run 1.tshift. So in the PB data set, so this is the first input here, this brick and head file, and we're writing the motion parameters to dfile.r01.1d. So here are the d files for runs 1, 2, and 3, and then at the end we put them all together. That's a little later on. So that's down here where we cat all three files to dfile rall. So for each run we do some registration stuff, and then at the end we concatenate the motion parameters just to have them all together. But you can look at one of these. 1D plot dfile.ro1, say, and there you go. Actually, if you're going to plot most things with multiple columns, you'll usually want to have separate scaling. And so each plot has its own scaling. And in the case of volreg parameters, we can tell 1D plot that these are motion parameters, and so it labels things for us. So beautiful. There's our big head motion at time point 42. And again, this is just one run of motion parameters. And we've already mentioned it, so I might as well continue and note that. So dfile underscore r all.1d is the catenated form that has all three runs. So here are the complete motion parameters with the three runs concatenated. So up to 150, here's run 1, 2, and 3. Roll, pitch, yaw, ISRLAP. Okay, so we save basically a time series of motion parameters in there, and then a time series of matrices here. So this should look, this is akin to the motion parameters, but these are matrices and not just the six parameters, three shifts and three rotations. This is these are 3x4 matrices. So mat dot, here are the mat run 1 volreg affine 12. If I just run less on that, it's just a whole bunch of numbers. But on each row, one single row it's wrapping around here is 12 numbers. That's a 3x4 matrix. But so we have a time series of transformations, and those are the two files that we really want here. We're going to apply the time series later on, and we'll need the motion parameters for excuse me, for like motion censoring and for regression. So I'll skip this all one data set for now, and I'll come back to it. The next thing we do, now we know how to align each one of our T-shift output volumes to the min outlier volume. We have that as a time series of transformations here. So we know how to align to that. We also know how to align our min outlier volume to the anatomy, and we also know how to align the anatomy to the template. In this case, those are all affine transformations, but whatever. Now we can concatenate them, put them all together. Since they are affines, we'll just use cat-matvec. And so the input to cat-matvec here, these are like nested functions, but so we'll read from the bottom up. So we have the time series of EPI transformations to the volreg base, concatenated with the inverse of the anat to EPI. So now that sends all that concatenation sends us all to alignment with the anatomy, and we'll also include the standard space transformation, and we'll redirect this. So cat-matvec is just going to dump all this to the screen as a text file, but then we'll use the Unix redirect symbol, and we'll save this to the warp affine 12.1d text file, and this again will be a time series of transformations that include all of these three transformations concatenated. So mat run 3, and the one with warp, so this is the run 1's time series of full transformations, full affine transformations that include the anatomy and standard space. So once we have those in a text file, let's apply them with 3D alineate. So 1D matrix apply, we're going to apply that time series of transformations, and the input is the T-shift data again. So we ran 3D volreg with the T-shift input, but we called the output junk because we didn't want to reinterpolate this. This would only be aligned with the min outlier. We want to go all the way to standard space, so we don't care about these results. We'll take the input from 3D T-shift again and apply our full concatenated transformation time series to that time series, and then now we have results that are fully aligned and in standard space. But it's not quite done, so we're still calling the output rm.something, because we're going to delete that too. Life is hard. So now let's go back and see why we might be deleting this. Well, here we look. Here we have an extra command. We create an all-one time series dataset. So 3D Calc dataset A is again the T-shift, but the computation to like what values we put in the output, the expression is just 1. So this is a time series where every value at every voxel at every time point is just 1. And the prefix is rm again, .epi.all1. So we create an all-one dataset. Then, so this alineate was to apply the concatenated transform to the EPI data. But then we have a second alineate. It's basically the identical command, except the input is now the all one time series. But we apply the same concatenated transformation to that. Why in the world do we do this? Well, basically, um, we want to map a full box of ones to the final space and see at what points in time do we lose data. So if we have a voxel that, because of head motion, has data at time points 7, 8, 9, 10, 11, 12, 13, 14, but then the subject moved, and due to that motion, uh, that location in space went outside the box, and so like the 3D volreg step kind of created new data there, but since it wasn't recorded, so this if the subject's head moves outside the box, then there's no data recorded for that same location in the brain. So after 3D volreg, you basically fill that location with 0 because the scanner didn't acquire data there. So that means you'll have data going up through time point 15, but at time point 16 now suddenly you have zeros. So you don't want to analyze that. That voxel is officially garbage. Even if most of the time series is great, you can't include these big spikes that go to 0, unless like a miracle occurs and that happens to be a censored time point. But in that case, we're not really looking for that. If you get really lucky and you lose only a censored time point, that might be you wouldn't really need to remove that volume. But ignoring that, we're just being conservative here, and so basically we're looking for voxels that don't have valid data at some point in time, and we don't want to analyze them. So we run 3D tstat-min because we want to find any voxel with something less than a 1. If the output isn't all ones, that means we've lost something. So after we do this per run, we run 3D mean, and then we look for where the mean is less than 1, and we create a data set called mask EPI extents. So this mask will contain a 1 everywhere that the time series is completely 1 at all time points across 3 runs of 450 time points. So this mask represents where we have valid data across all 3 runs. And now we can finally make the real volreg output. So for each run we run 3D calc. We'll take that result from alineate above, so RM EPI no mask, that's the first alineate result. So that's what we created with the T-shift output. But now we take that result and we multiply it by the mask. So if data set B is the mask, we simply take A times B, because the B values are either 0 or 1. The step expression is either 0 or 1. So basically you just remove voxels that don't have data across all time points, valid data. And that's the extents mask. That's the one mask that we automatically apply in AFNI Proc. And that's it. And then we do a couple little extra things. We use cat matvec to just to grab everything but volreg, and we can use that to map to warp our min outlier volume to the standard space, just to have a copy of that in standard space. And we actually also run 3D copy on the anat, the anat in standard space, and we just call it anat final. This is just making an extra data set. Why? Because anat final, people can look at a directory and know what it means. It's the anatomy that's in your final space that your final EPI and stats should be registered with. And then you don't have to guess, well, is the def t anat ns? That's harder. So We just make a convenience data set so that you're sure what you should be working with. And we make a record of the cost functions to see how how what they were for registration in case we need it for quality control to see if there's any issue. And then one last data set that we create is we run 3D Alineate on the FT anat, and we warp that to standard space as well. This is another QC volume that I like to have. It puts the anat in standard space, but it still has a skull. Sometimes when we're pondering registration or strange blobs of apparent bold activity, we want to know, and they're slightly outside the brain, we want to understand, are we in CSF or what? So it's nice to be able to look at a sculled version of the anatomy as well. And then the final step in the volreg block, as we did above in the T-shift block, we requested, if you recall, if I cat SO5, how do you spell S05? At the top of our AFNI proc command, we had the option radial correlate blocks. We asked to run radial correlate at the ends of tcat and the volreg blocks. And so here we're doing at the end of the volreg block. And we'll look at that result later with the rest of the QC. So now let's see how this looks in AFNI. So I'll lower a couple windows. In the bottom controller, we're looking at the T-shift output. Top controller, controller A, is looking at the tcat output. So let's change controller A's dataset now to be the output from 3D volreg. So let's set our actually, are we at the same place that we're supposed to be if we jump to XYZ? Okay, so just to start at where we're supposed to start, if we switch our underlay now to run 1 volreg, processing block 2, run 1 volreg, you notice a few things right off the bat. So here's the T-shift. There is the standard space. There's the original space T-shift result, and this is simply registered to the EPI base and then to the anatomy and then to standard space. So all those transformations combined into one, and this is the resulting volume at time point 0, the first time point of the first run. So you notice a few things. One, the volume on top, if you can see it well, it's blurrier than the volume on bottom, and of course it is. That's one of the penalties for applying any transformation to the data. Now that means you have to resample it. The voxel grid down here on the bottom was 2.75 millimeters in plane by 3 across planes. To get a data value at the current crosshair location, you have to map that location, inverse map that back to a ridge space, and see where you are in the tcat, the T-shift volume. But you're going to be somewhere in the middle of some set of 8 voxels. Perhaps by some miracle you could land on one of them, and then you'll get the exact same value. But in general, you'll be somewhere in the middle of 8 voxel centers. If you picture this grid as a bunch of shoeboxes with the voxel coordinates being the center of each shoebox, if you make a 2 by 2 by 2 set of shoeboxes, this voxel center will be in there somewhere in the middle of those 8 centers. So based on the distance from this center to the 8 neighboring centers, you'll get some sort of interpolated value, and so you're blurring values together. So this result will almost always be a blurred version of that one. You also notice it's wider. This is the original space subjects EPI data. This is the standard space. Why is it wider or shorter, or however you want to call it? because the template looks like this. So the subject's brain is relatively narrower than the template, so it had to be squished or stretched, depending on which way you want to picture it, to match. So, so when you're going between orig space coordinates and the final space coordinates, they won't be an exact match. You notice on the bottom we're a little bit interior of the brain, and on the top we're at the very edge. So it's not exactly the same space in the anatomy, because the uh, the the coordinate interpolation might be correct, but then you've got to include the fact that now the EPI is aligned with the anatomy and the anatomy is aligned with the template, so it's squeezed and stretched in different directions, and you're not at the same location in the brain. Here in the ridge space and the T-shift output, we see a clear bold signal there. Now in the result, we see garbage with a huge motion spike because we're at the very edge of the brain. So let's find a slightly better location. We'll just move a little anterior. Notice that, again, this box corresponds to this 3x3 grid. So this is 9 voxels in this green box corresponding to these 9. So if I click upward and like move one voxel, we're moving in the anterior direction, towards the anterior. So we can find a better location that we're happy with, and okay, this is great. Or let's, yeah, that's fine. So let's use this time series as our new one, and we can all jump to that location if you're following along. So the coordinates now are 24, 86, 14 approximately. So we can, in the top controller, controller A, if we right click in the image window, we can jump to XYZ, and we'll forget about these original space coordinates. Now we have standard space 1, we'll say 24 space 86 space 14. And I apply and miraculously go nowhere because I'm already at those coordinates. So again, the AFNI GUI takes these and rounds these coordinates to the nearest voxel center. So it's actually as if you had typed in the more precise ones. If we saw better correspondence between these two volumes, like if I jump here, I don't know if any spot looks a little more similar. A couple things we can't really tell. A couple things you would notice is that the time series ought to look similar if we were in the exact same corresponding location, except the one on top you would hope is a little cleaner. I'll just jump back. Is a little cleaner because this voxel's time series is averaged from the 8 neighbors in original space. So there should be some noise cancellation you would hope for, and this, the signal would overlap and the noise would cancel a bit, so you'd hope to get a slightly cleaner volume time series. Any spikes that are in any of the 8 voxels down here that are used to create this time series will appear in this time series. So, combining them is good and bad. You generally can't hope for noise cancellation to work on a large spike. That's just almost impossibly unlikely. So for better or worse, we get a time series here, but of course spikes hopefully are due to motions that are big enough that will censor them, and hopefully you get a slightly cleaner time series and a blurrier volume here. But now we are in standard space. So let me stop at this point, and then we'll just continue in a bit.